Hey everyone and welcome. Today we're diving into a Leetcode problem called Distribute Candies Among Children II. It sounds sweet, right? We'll break down what it's asking, and then explore a couple of ways to solve it. Don't worry, we'll take it step by step. Alright, so here's the problem. We're given two positive numbers, which is the total number of candies we have, and which is the maximum number of candies any single child can receive. Our job is to figure out the total number of ways we can distribute these candies among exactly 3 children. The main rule is that no child can end up with more candies than the... Let's look at an example. Suppose we have equals 5 candies, and the sack here is 2 candies per child. How many ways can we do this? Well, if child 1 gets 1 candy, then 4 candies are left. Child 2 could get 2 candies, that's within the limit, leaving 2 for child 3, also within the limit. So, 1, 2, 2 is a valid way. What if child 1 gets 2 candies? 3 candies are left. Child 2 could get 1 candy, child 3 gets 2. That's 2, 1, 2. Or child 2 could get 2 candies. Child 3 gets 1. That's 2, 2, 1. Are there any other ways? If child 1 gets 0, we have 5 candies left for 2 children, with a limit of 2 each. That's not possible, because 2 plus 2 is 4, not 5. If child 1 gets more than 2, that violates the limit. So it looks like there are 3 ways: 1, 2, 2, 2, 1, 2, and 2, 2, 1. The output is 3. Makes sense? Let's try another one. Equals 3 candies, and the task is also 3. This time, since the limit is high enough, it doesn't really restrict us much for just 3 candies. Child 1 could get 0. Then we need to distribute 3 candies between child 2 and child 3. That could be 0, 0, 3, 0, 1, 2, 0, 2, 1, or 0, 3, 0. That's 4 ways. If child 1 gets 1 candy, 2 are left. That could be 1, 0, 2, 1, 1, 1, or 1, 2, 0. 3 ways. If child 1 gets 2 candies, 1 is left. That could be 2, 0, 1, or 2, 1, 0. 2 ways. And if child 1 gets 3 candies, 0 are left. So, 3, 0, 0, 1 way. Adding those up, 4 plus 3 plus 2 plus 1 gives us 10 ways. And indeed, the output is 10. Okay, so how can we systematically count these ways? The first idea that might pop into our heads is just to try out all the possibilities for the first 2 children. Let's say the first child gets some number of candies. Let's call it C1. Then, the second child gets C2 candies. Once we've decided on C1 and C2, the number of candies for the third child, C3, is fixed, right? It has to be the total minus C1 minus C2. Then, we just need to make sure that each of these amounts, C1, C2 and C3, is not negative and also not more than the Pleiadian Borley-Winers. So for child 1, the number of candies they get, let's use for this, can range from 0 up to the smaller of the total candies, or they can't get more than candies in total, obviously, and they can't get more than. Then, for child 2, let's use for their candies. This can range from 0 up to the smaller of n minus I, which is the candies remaining after child 1 took theirs, or the candies for child 3, let's call it, will simply be minus minus. If this value is also between 0 and inclusive, then we've found a valid combination. And here's how that logic looks in Python code. We initialize an answer variable, let's call it to 0. Then we have our first loop for the candies for child 1. It goes from 0 up to minimum of n and limit, inclusive. Inside that, a second loop for candies for child 2. It goes from 0 up to inclusive. Then we calculate the candies for child 3 as minus I minus j. Finally, we check if quote 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 quote. So how fast is this enumeration approach? The outer loop for child 1's candies can run, in the worst case, about times. And the inner loop for child 2's candies can also run about times. So altogether, the number of operations is roughly multiplied by, we call this big O of limit squared or order limit squared time complexity. What about memory? We're just using a few variables like and, so the space complexity is order 1 or constant space, which is pretty good. However, given that can be up to 10 to the power of 6, limit squared could be 10 to the power of 12, which is likely too slow. We probably need something more efficient. Alright, let's think about a more advanced mathematical way to solve this. This uses a cool idea called the Principle of Inclusion-Exclusion. Here's the gist. First, imagine there's no upper. How many ways can we distribute candies to 3 children? Let's call this our total. But this total includes ways where 1 or more children get too many candies, more than. So we need to subtract those. We'll find the number of ways where at least one child violates the limit, and subtract that. But if we do that, we might have double subtracted cases where 2 children violate the limit. So we need to add those cases back in. And then, we might have overcorrected for cases where all 3 children violate the limit, so we subtract those out again. It's a bit of a back and forth, but it helps us zero in on the correct count. To count these ways, especially the no upper limit part, we use a concept from Combinatorics, often called stars and bars. If you want to distribute identical items like our candies into distinct bins, our children, the formula for the number of ways is quote, k plus m minus 1, choose m minus 1. In our case we have 3 children, so is 3. The formula becomes quote, k plus 3 minus 1, choose 3 minus 1, which simplifies to k plus 2, choose 2. This k plus 2, choose 2 can be calculated as k plus 2 times k plus 1, all divided by 2, assuming is not negative. We'll use a helper function for this. Let's define a helper, say that takes a number of candies, let's call it, and returns quote, num underscore candies plus 2 choose 2. This is our basic building block. First, the total unrestricted ways. This is just count underscore combinations underscore for underscore candies applied to n. Second, subtract cases where at least one child gets more than candies. This means they get at least limit plus 1 candies. So we pick one child. There are 3 ways to do this. We give them limit plus 1 candies. The number of candies left is minus the quantity, limit plus 1. We then distribute these remaining candies among the 3 children using our helper function. So we subtract 3 times count underscore combinations underscore for underscore candies applied to n minus limit minus 1. Third, add back cases where at least 2 children get more than we pick 2 children. 3 ways to do this. Give each of them limit plus 1 candies. The remaining candies are minus 2 times the quantity limit plus 1. Distribute these using our helper. So we add back 3 times quote count underscore combinations underscore for underscore candies applied to n linif remay. The waratan is 2 times limit minus 2. Fourth, subtract cases where all 3 children get more than give each child limit plus 1 candies. Remaining candies are minus 3 times the quantity limit plus 1. Distribute these, so we subtract count underscore combinations underscore for underscore candies applied to n minus 3 times limit minus 3. And here's the Python code for the inclusion-exclusion principle. First we define that helper function, let's call it. It takes the number of quote candies to distribute. If this number is negative, it's impossible. So we return 0. Otherwise, it calculates candies to distribute plus 2 times candies to distribute plus 1, all divided by 2. This is our ck plus 2 formula. Then, for the main calculation, the answer starts as count underscore ways of n. Then we subtract 3 times count underscore ways of n minus the quantity limit plus 1. Next, we add 3 times count underscore ways of n minus 2 times the quantity limit plus 1. Finally, we subtract count underscore ways of n minus 3 times the quantity limit plus 1. And that gives us our final answer. Now let's talk about efficiency for this inclusion-exclusion method. Our helper function does a few simple arithmetic operations, a couple of additions, a multiplication, and a division. That's constant time. And in our main calculation, we call this helper function exactly 4 times. It doesn't matter how big or r, it's always 4 calls. So the total time complexity is big O of 1, or order 1. That means it takes a constant amount of time. This is super fast and will easily pass even with large inputs. For space, again, we're just using a few variables. So the space complexity is also order 1, or constant space. This is a huge improvement over the order limit squared enumeration method. So to wrap things up, we tackled the problem of distributing candies to 3 children, with each child getting at most candies. The first approach, enumeration, was straightforward. Just loop through possibilities for the first 2 children and check the third. But it was too slow, with order limit squared time complexity. The second, much more efficient approach, used the principle of inclusion-exclusion. It started by counting all ways without any limit, using a stars and bars idea, then carefully subtracted cases where 1 child got too many, added back cases where 2 children got too many, and finally subtracted cases where all 3 got too many. This clever math got us to an order 1 solution, super fast. Hope that explanation made sense and helped you understand both the problem and the different ways to approach it. If this was useful, please hit that like button, consider subscribing for more Leetcode breakdowns, and feel free to drop any questions or comments below. Keep practicing, keep coding, and I'll catch you in the next one.